I'd like to introduce our next speaker now, and he is Dr. Robert Hoye from the University of Oxford. And he's going to talk to us today about going beyond lead-halide perovskites. What's next for photovoltaics? Thank you, Robert.
Thank you very much for the kind introduction, and also thank you very much to the advisory board for giving me the opportunity to come here and talk about the work from my group. And I also like to thank D.D. Summer for giving quite a fantastic introduction to the lead-halide perovskites, which I'm going to make use of to spring from to talk about how we can go beyond these materials and learn from halide perovskites to identify alternative classes of materials which are stable and which are lead-free, but which can replicate some of the exceptional optoelectronic properties that we find. But very briefly, just want to introduce my group. So we're based in the chemistry department at Oxford. And in addition to having chemists, we have people from a range of different backgrounds and different nationalities as well. So we have chemists, we have material scientists, physicists, and engineers, and we're working together on developing optoelectronic materials. And my group's research spans from fundamentals through to applications. So we have an ERC grant, which is on a high-risk materials discovery project to develop energy harvesting materials for Internet of Things applications. But we'll also have funding from the Royal Academy of Engineering focusing on new kinds of medical imaging technologies. Plus, we have collaborations with companies like First Solar as well. So this is some of the recent work from my group. And in today's talk, I'll be focusing on talking about defect tolerance and how we can understand this and use this to discover new kinds of materials. And also very briefly about our recent applications on radiation detectors from some of the new materials that we found, such as bismuth oxyiodide. But some of the other things we've done include applying these materials for solar fuels, so making inorganic artificial leaves for harvesting sunlight to split water to make green hydrogen, and also applying the device structure we made for perovskite photoelectrochemical tandem devices. And very recently, in collaboration with Judith, we've created this spin-off company called Nanoprint, which is commercializing a spatial atomic layer deposition reactor, which can think of as a metal oxide printer. And this is currently based in the Cavendish Laboratory in Cambridge. OK, so you saw this slide from D.D. Summer's talk, summarizing the development of a range of different technologies. And I just want to zoom in into this bottom right-hand corner here, which focuses on the emerging technologies. And in fact, this is not so low now. So the yellow points, the yellow circles, corresponds to perovskite solar cells. And it really is quite remarkable that now the record efficiency is 26.1%, which is a few decimal points away from the record efficiency for a single crystalline silicon solar cell, which is 26.8%. And I think we just to take a moment to realize how remarkable it is that a solution process polycrystalline device could be almost as efficient as a single crystalline silicon device that's processed at much higher temperatures. And what's also important is that the perovskites absorb at a complementary part of the solar spectrum to silicon cells. So you can put them together to make tandem photovoltaics. And that's what's represented by these blue triangles here. And you can see the current record efficiency is held by a Chinese company called Longji, which now has 33.9% certified efficiency. And this is not only greater than the best efficiency for single-junction silicon-based device, it's also the most efficient two-terminal tandem out of any material under non-concentrated solar illumination. But of course, the problem is that it has lead. Perovskites contain lead, which is easily accessible because this material is water-soluble. And there are quite polarized views in the community about whether that really is a problem for commercialization. So I'm not going to talk about these different viewpoints, but what is also important is whether we can learn what is it that make these halide perovskites work so well, and whether we can apply them to discover new kinds of materials, especially materials which are stable and non-toxic as well. So within the wider community, there's in general, three different approaches to addressing this problem. The first is through chemical analogy, substituting out divalent lead for other divalent cations, such as tin perovskites. Another is through structural analogy, for example, working on double perovskites or other kinds of perovskite compounds. halide perovskite compounds. And the third is electronic analogy, which is something I'll talk a bit more about. Okay, so the first section is focusing on this concept of defect tolerance. So a solar cell needs to absorb light, and it then needs to transport the photo-generated electron holes out of the active layers. So it needs to have, when we think about just developing new solar absorbers, we need to talk about the band gap and the absorption coefficient, but we also need to think about the charge carrier transfer properties, in particular, the mobility and the lifetime. So what I'm showing in this slide is a model that was proposed almost 10 years ago, looking at defect tolerance. And many people believe that this is a property that the lead-halide perovskites possess, which is key to its exceptional performance. So if we look at a traditional defect-sensitive material, for example, silicon, which is a classic example, this materials tend to form deep traps within the band gap. And so we have to make this material with very low densities of defects, down to 10 to the 8 per centimeter cubed, in order for these devices to be efficient. Now, to make a fair comparison, I'm looking at the efficiencies of polycrystalline silicon devices. I want to make a fair comparison with polycrystalline lead-halide perovskites, which have much higher efficiency, despite having millions of times more defects. And this model here proposes why this might be the case, why we can have more defects in perovskites, but still be more efficient. So if we look at traditional semiconductors, we form a bonding and anti-bonding state across the band gap. And when we form defect states, for example, silicon vacancies, they tend to form close to where the original atomic orbitals were, in this case, close to the middle of the band gap. So deep trap states have an equal or very similar likelihood of capturing both an electron from the conduction band and a hole from the valence band. And so we have very high rates of non-radiative recombination. And really, the only way to get around that is to get rid of these defect states as much as possible by processing these with high temperatures, have very perfect materials. By contrast, the lead-halide perovskites have a very different electronic structure, where instead we have this antibonding to antibonding orbital transition across the band gap. And you can see in this case here, the original atomic orbitals are within the band or close to the band, rather than in the middle of the band gap. And so when we form point defects such as iodine vacancies or lead vacancies, there's a much greater likelihood now that these trap states will be shallow rather than deep. So for example, if we look at this defect state here, it can very easily capture an electron from the conduction band. Because it's so far away energetically from the valence band, it has a much lower likelihood of capturing a hole. And therefore, the likelihood of non-radiative recombination becomes much lower because of these shallow states. And we believe that this happens because of the quite unusual electronic structure that these halide perovskites possess. And this would then imply that we can find defect-tolerant semiconductors that behave in a similar way if we can find electronically analogous materials that form a very similar electronic structure, and not necessarily be limited to just halide perovskites, other kinds of perovskites. And so if we look at the periodic table, one of the elements that stands out a bit here is bismuth. This bismuth is right next to lead. It has a stable 3+ oxidation state, which means lead has the same electronic configuration as lead's 2+ cations. But it's the green element in poisonous corridor, because to the left, we have the toxic elements, and to the right, we have the radioactive elements. But bismuth is neither toxic nor radioactive. For example, if you look at lead tin solder, people are replacing the lead in the solder with bismuth tin. Or if you use bismuth oxychloride, this is used for cosmetics, because there's no known evidence for toxicity. So perhaps with bismuth-based compounds, we have a chance of finding materials that could be defect-tolerant, but which can also be stable and non-toxic as well. And this is one example that we've worked on together with Judith Driscoll's group, bismuth oxyiodide, which we grew by chemical vapor deposition. And over here, we had a collaboration with Vladan Stevanovic at the National Renewable Energy Lab to do some defect calculations on these materials, looking at the point defects. So here you can see the list of the vacancy and anti-site defects that we considered. And this is a bit of many things happening on this diagram. So let's look at the simplification of this on the left-hand side here. So here you can see that these are the 4 most common point defects expected to form in this material. And that's because these have the lowest formation energies. And the dashed lines here represent the transition levels, which is where these lines change in slope, because that's where these point defects can capture an electron hole. So you can consider these to be where the trap levels are located. And if you look at this, you can see that for most of these defects here, they're located within the bands, or in this case, for the bismuth vacancy, it's shallow within the band gap. And this confirms that the hypothesis is consistent with the hypothesis that we put forward, and would suggest that this material is indeed defect tolerant. So to test this experimentally, it's quite challenging to do that because we're looking at usually very low densities of defects, which is difficult to measure. So here we're to test experimentally whether bismuth oxyidide is defect tolerant and how defect tolerant it is. We were inspired by this paper from NREL, published in ACS Energy Letters a few years ago. What they did here was they put their perovskites into an XPS vacuum chamber and radiated it with X-rays for 24 hours under vacuum. You can see that that led to a removal of the iodine, removed as methylammonium iodide. And then monitored, as more iodine was removed from the perovskites, what that did then to the electronic structure. So here they're monitoring in the same interaction volume, the valence band to fermi level offset. And you can see here that there's a certain region, certain iodine to lead ratio, where there was no change in the fermi level. And it was only above a certain region that changed. So this is a way to probe how defect tolerant materials are experimentally. So we did something similar for bismuth oxyidide. We put these materials into a furnace, heated very gently 100 degrees Celsius under vacuum to intentionally remove, change the surface stoichiometry. So the dashed lines represent the original stoichiometry, and it's very close to being a 1-to-1-to-1 ratio between bismuth, iodine, oxygen. And you can see that as we heated this over time, we were removing a lot of iodine, and we're removing bismuth. And that's because bismuth and iodine vacancies have the lowest formation energy. And because we're removing those two, the fraction of oxygen is increasing. But within the same interaction volume, we can see that the fermi level to valence band offset remains exactly the same over the entire region here. And also the bismuth core levels remains unchanged in terms of binding energy and also in terms of the forward half maximum. And this is consistent with what we would have expected based off the defect calculations. Because here, the crossover point between the lowest formation energy donor defect, which is this iodine vacancy, and the lowest formation energy acceptor defect, which is this bismuth vacancy, that crosses over close to the middle of the band gap. So this is an intrinsic semiconductor. And that would imply that this is a self-compensating system, where if you remove some iodine vacancies, you also remove some bismuth vacancies, and overall, the fermi level will remain in the middle of the band gap. And that's indeed what we see over here. And we can monitor how this affects the charge carrier lifetime of these materials. So to do this, we used transient absorption spectroscopy, where we saw that despite changing the surface stoichiometry at the percent level, there was no significant change in the decay in the photo-generated charge carriers. But at the same time, so that fundamentally looks quite interesting. But if we look at photovoltaic devices from bismuth oxyidide and other kinds of bismuth and antimony-containing compounds, you can see that lead-halide perovskite over here, and this was published a few years ago. It was over here, but this is where bismuth and antimony-based compounds are. They're a lot less efficient than lead-halide perovskites. So then we want to try to understand why that is, and whether defect tolerance can be found in all these bismuth-based compounds, or whether there's other factors involved which also play an important role. So this is a recent commentary that I wrote about with Aaron Walsh and David Scanlon, along with Alex Ganoz. So together, experimental and theoretical viewpoint around defect tolerance, some of the other factors that could be involved. And one of those is the band gap, because if you look at halide perovskites, the defect tolerance that people talk about and find in the iodide-based compounds isn't maintained as you go across the series. As you go towards bromide and chloride-based perovskites, the halide vacancies become deeper and deeper. And for people who worked on perovskite nanocrystals, as you change the composition of the halogen site, what people find is the photoluminescence quantum yield, or the PLQE, drops out quite substantially. And this is because as you increase the band gap and decrease the lattice constant, there's a greater likelihood that an iodine vacancy is going to be deep within the band gap. Also, it means that your lead-lead dangling bonds are closer together, going to interact more strongly. So the ionicity of these, the metal cation and the halogen bonds, that plays an important role that we need to consider. And here we can see, this is taking some data from the materials project database. So looking at across a lot of different materials, we can see that as you increase the band gap, the electronic dielectric constant decreases. And that means that the ability of your material to coulombically screen out charge defect states becomes lower. And therefore, there's a greater likelihood that charge defect states can capture electron holes. And also the effective mass increases as well. So this also makes it more challenging to maintain defect tolerance. And band gap is an important factor. And there's other factors as well, but we don't really have time to talk about that. But I want to talk about another property, because so far we've been talking about defect tolerance, which mostly relates to the recombination rate. And that affects the charge carrier transport. But what also affects charge carrier transport is mobility as well. And up to this point, an inherent assumption we've been making is that the mobilities across all these different compounds isn't so strongly affected. And recently what we've been discovering is that assumption doesn't necessarily hold in all cases. So this is quite a nice work we did with Tony Cheatham a few years ago on looking at cesium silver bismuth bromide double perovskites. And what we observed, and what other groups observed as well, is that if you look at the decay in the photogenerated charge carriers, the time constant for that is very long. So we have a time constant of 1.4 microseconds. So to put this into context, with lead-halide perovskites, which are considered to have rather low recombination rates, that only has a lifetime of 100 nanoseconds. So here we have an order of magnitude longer lifetime, which would suggest that this material has quite good charge carrier transport properties. But then when people make devices and measure the diffusion length, it's actually only 30 nanometers. So that implies that the mobility is actually very low in these materials. And another thing we can observe here is that the photoluminescence peak in red is redshifted compared to the absorption peak. And in the time since when we published this work, the realization that people have made in the field is that this material undergoes a process called carrier localization. So I'll talk about what that means. So here we have two different pictures to look at recombination in semiconductor materials. And in the first part of the talk where I was talking about defect tolerance, I was really referring to this electronic picture, where we have a plot of energy against wave vector k, and we have bands which are dispersed, and the inverse of the curvature relates to the effective mass. And then we can imagine trap states just being flat bands within the band gap. So this is our picture for imagining how trap states can affect the lifetime. But at the same time, the atoms within the lattice are vibrating at room temperature. So we have phonons which are present. And these phonons can couple to the charge carriers. And so sometimes the coupling is so strong that the behavior, the charge carrier kinetics of the material aren't so well described anymore by this electronic picture. And we have to go towards this polaronic picture. So in this picture here, I have energy against Q, where Q represents the average displacement of atoms from their equilibrium positions. So here we have, on the bottom U-shaped curve, it represents the energy of your lattice in the ground state. And then if you photoexcite, you then increase this energy up to the excited state here. So you can see that the energy of the lattice changes as you distort atoms from equilibrium due to the population of the phonon modes which are present. And sometimes what can happen is that in the excited state, charge carriers can relax into the self-trapped exciton state, where the charge carriers are then localized in space, and then it's very difficult for them to be transported. And this is how the mobility could be substantially smaller than what you would predict from the effective mass. And we can look at what affects the likelihood of this carrier localization. So we look at the energy barrier from free carriers here. So I should mention lambda is a dimensionless parameter that is a ratio of the lattice parameter divided by the radial extent of the wave function. So if that radial extent of the wave function is infinite because we have free carriers, then we're over here. Whereas if we have localized carriers, then we're over here. So if you have a 3D material, then you have this energy barrier between free carriers and localized carriers. So that then reduces the likelihood of having carrier localization. But then if the electronic dimensionality reduces, so it reduces to 2D and then to 1D, then this energy barrier disappears and essentially goes to nothing. And so carrier localization then becomes thermodynamically favorable as you lower the dimensionality of these compounds. And this is a picture of what carrier localization means. So you can imagine if your charge carrier is interacting with optical phonons, then sometimes that means that your wave function of your polaron is delocalized over several unit cells. And that we call a large polaron, where mobility can be quite substantial. But then if there's a strong coupling with optical phonons, or if there's coupling with acoustic phonons, then this wave function can be reduced to within a unit cell. And then the only way your polaron can then move is by hopping between different lattice sites. And that's why there can be a substantial drop in the mobility. So we're going to have a look at, over the past few years, this paralocalization process has been found to be extremely prevalent among bismuth halide compounds. In fact, it's been found to be so prevalent, some people are even labeling this a hallmark of these materials. So in the rest of the talk, I wanted to first of all go into a bit more detail about what this problem is and what it means. And then I'll talk about some of our recent work where we found a way to overcome this problem. So to illustrate what this means, I'm going to talk about a recent class of bismuth-based compounds, ternary bismuth-based compounds, that's been gaining quite a lot of interest in the photovoltaics field. And it's really driven by some recent work on silver bismuth sulfide, which has efficiencies which are now above 10%. This is a bit, in the time since this work was published, there's been some further developments. So that is actually one of the most efficient bismuth-based materials in solar cells. And we were interested in looking within this space. So one of the issues with silver is that it's expensive, and silver plus cations can be toxic to aquatic life. So we want to investigate the related compound, sodium bismuth sulfide, because sodium is, you can just find that in table salts. You can see that this has quite an interesting structure here, where instead of the sodium and the bismuth occupying different lattice sites, they occupy the same lattice site. We call this cation disordered. So we're interested to investigate this material because of using benign and abundant sodium, as I mentioned, but also because we're interested in looking at these materials from the perspective of defect tolerance. And sodium we expect to act as a spectator ion at the band extremer. So unlike silver, we don't expect it to contribute any states to the band extremer. And therefore, we mostly have bismuth-sulfur interaction, which is quite similar to the electronic structure, qualitatively similar to the electronic structure of perovskites. At the same time, sodium and silver have the same ion radii, and that means we get this high symmetry crystal structure, which is quite different to the low symmetry crystal structures that we find quite often with bismuth-based bismuth halide compounds. So this is a work that was led by one of my postdocs now, Etang, working together with Sean Kavanagh, who just finished his PhD, with David Scallon and Aaron Walsh. So this is a joint experimental computational investigation into this material. So the first point we want to make here is that this material is very stable in air. And we tested this and put this in the paper after storing these materials for 112 days. After we went through peer review, so 11 months, we measured the material again, it's still the same phase. So this material is very stable in ambient air, which is quite a big contrast to hybrid halide perovskites. And another important and interesting feature that this material is a very strong light absorber. So you can see from this plot of this blue line here, which represents the absorption coefficient for sodium bismuth sulfide, it's a lot higher than what you find in methyl lead-halide perovskite and other established thin film materials. So what that means is that if we can calculate what that means in terms of the optical limit and the efficiency, that means that you can just use a material that's only 30 nanometers thick and still, in principle, achieve an efficiency of 26%. So this can be quite promising for making very thin, lightweight solar cells. I should mention this is a predicted efficiency limit rather than something that we've demonstrated experimentally. But what we ought to understand more about the charge carrier transport properties. So here, Sean calculated the energy versus K diagram. And you can see that we have a reasonably dispersed conduction band, a somewhat flatter valence band. But what's quite unusual about this material is that we see these three bands forming within the band gap. And I should mention, in these calculations, there were no defects in the calculations. So these don't arise due to defects, but they arise due to the intrinsic structure of the material itself. And here, this is a plot of the density of states a map of denser states in real space, so y-axis versus x-axis, you can see that there's a high cluster over here. And this cluster over here occurs when there's strong coordination of sodiums around the sulfur. Because, as I mentioned earlier, the sodium and the bismuth, they occupy the same lattice site. But when we grow these nanocrystals kinetically, they aren't necessarily organized in a uniform and homogeneous manner. So we get clusters of sodiums and clusters of bismuth. And what we find is that these localized sulfur peace states form when there's strong coordination of sodiums forming around the sulfurs. And that makes sense because the sodium does indeed act as a spectator ion at the band extremer. And so at the band extreme, the bismuth has nothing to bond to. And so it almost forms these states which almost look like defect states here. So we want to understand what that does in terms of charge carrier kinetics. So again, we used transient absorption spectroscopy, which allows us to monitor the population of photoexcited charge carriers. And so here you can see we get these two peaks in the spectra, which roughly agree with the band gap of the material. And here you can monitor the kinetics. So this tracks the decay in the charge carriers. And look at the time scale here. This is in microseconds. So the lifetime is about 5 microseconds, which is a lot larger than the lifetime of perovskites, which is 100 nanoseconds. And this looks quite interesting. So we want to understand this a bit more. So in the previous slide, this is what we called long-time TA, where we use a pump probe delay stage on a longer time scale. Here we looked with finer time resolution on the picosecond time scale. And we see this negative signal, which is called photo-induced absorption, but we can deconvolute this to get the ground state bleached, the carriers in the excited state. And when we look at the kinetics, we have this decay here that's only 34 picoseconds, which is not captured in a long time decay. So there's something that's really quite unusual that's happening with this material. To understand this in more detail, we collaborated with Laura Hertz in physics department at Oxford, who has this technique called optical pump terahertz probe spectroscopy. And what this does is that it allows you to monitor the photoconductivity of your material with picosecond time resolution. So what you can see here is that we get this signal after photo excitation, and then the photoconductivity drops off very rapidly. And in fact, the localization rate is 2.5 picosecond. And for context, if we look at these double perovskites here, the localization rate is only 1 per picosecond. And we know that there is quite strong carrier localization in these materials, and that will also suggest there's very strong carrier localization in sodium bismuth sulfide as well. And you can see that after carrier localization, mobility drops by an order of magnitude to 0.03 centimeters squared per volt second. So we want to understand why this will happen. And carrier localization happens due to coupling to phonons. And that can be either large polarons, forming large polarons, or small polarons. So to understand the strength of the coupling with optical phonons to form large polarons, we calculate the Froelich coupling constant. And for those of you who aren't familiar with this, if the Froelich coupling constant is greater than 10, that's strong enough coupling for carrier localization to take place. But you can see here that that wasn't the case. These coupling constants are quite low. So then to understand where the small polarons form, what Sean did here in these calculations was he introduced an electron to the lattice and then relaxed it, or he introduced a hole to the lattice and relaxed it. And what we found here was that the holes tend to cluster around these sulfurs, which have high coordinations of sodium. And if you think back earlier, that is where we have these localized sulfur peace states. So what we propose from this is that these quite flat bands due to the localized sulfur peace states will capture holes very quickly after photoexcitation. And then the lattice can then relax around that due to acoustic phonons, thus forming a small polaron. And there's some degree of carrier localization for the electrons as well, which tend to cluster around the bismuth. So this explains why in this material we actually don't see any photoluminescence, because there's a very small likelihood that the electron hole can find each other because they're localized away from each other spatially. And also explains why the lifetime is so low in these materials, because there's a very small likelihood that both an electron and hole can find the same defect state and recombine. So that sort of explains to you the problem with carrier localization bismuth-based materials. I'll very briefly cover a recent solution we found with bismuth oxyiodide. I just want to briefly mention that we have been working on this material for some time now, firstly for solar cells, and then for indoor photovoltaics, and also more recently for solar fuels. But in this application here, we want to understand the fundamental properties of single crystals of this material. So this is a project led by former student of Judith and myself, Rob Yacht. Very clever guy. He made these single crystals with very low defect densities, as you can see here. So we want to eliminate any effects from defect states and just understand the fundamental carrier phonon properties of this material. So here you can see the PL decay curves of this material as a function of temperature. So going from room temperature through to 80 Kelvin. And at room temperature, PL decay is so fast compared to all these others that you can't really see it in detail. Very strangely, the PL lifetime is just 2 nanoseconds. And that's the same PL lifetime as we get in thin films. So despite decreasing the defect density by 6 orders of magnitude and going from thin films to single crystals, we still have the same PL lifetime. And that tells us there's something quite strange happening with this material. And what's equally strange is that when we cool this single crystal down, in the same material, we have the lifetime increasing up to 6.8 microseconds just by cooling down the temperature. So to understand this in detail, we again did transient absorption spectroscopy. And here in these ground state bleach decay curves, you can see that we have very strong oscillations, which are damped. And this is a characteristic of the generation of coherent phonons. So you photoexcite the lattice, and in photoexciting this material, the electron holes induce phonon modes which take place, which then couple to these electron holes, giving rise to these damped oscillations. So what we can do, we can fit the ground state bleach decay and fit a damped sinusoidal function to these oscillations. And by taking a fast Fourier transform, we get these 2 peaks appearing, and these 2 peaks agree with the 2 A1G mode peaks we see in the Raman spectra. So that tells us that we're inducing these 2 symmetric intralayer breathing modes. And these are only induced if we photoexcite above the bandgap 1.9 eV. So that tells us that this is not impulsive Raman scattering, but rather displacive excited coherent phonons. So knowing what the main phonon modes are that these charge carriers couple to, we could go to our theory colleagues, in this case, Ivana Bravich and Timur Montserrat in Cambridge, and simulate what happens to the energy of the lattice as we distort along these 2 phonon modes that you see here. So this is a map of the excited state, and you can see that there's this local energy minimum. So if we go to that point here, we can look at what happens to the exciton. Now this is a 6-dimensional function, so we can't really put that into this slide. So what you can see here is a 2-dimensional projection of this 6-dimensional function. And you can see that the electron wave function and the whole wave function of the exciton is completely spread out across the entire lattice we analyzed. And that tells us that there is no carrier localization in this material. So then we can take a cross-section along here in the energy map and get this blue line in this energy versus Q diagram or configuration coordinate diagram. And we can do the same thing for the ground state as well. Now, very interestingly, so these were GW cal, very high energy, high level calculation. I mean, this band gap here exactly corresponded with the band gap we measured at 4 Kelvin. So that was a very close calculation. What we also predict from this CC diagram is that because the ground state increases so much, the photoluminescence will be redshifted compared to the optical absorption. And that's indeed what we see. So to explain what these trends in these PL decay curves, this is our proposed mechanism, where at room temperature, the population of phonon modes is such that we can get high Q values such that excited charge carriers can go over here and then directly enter the ground state. And then entering a ground state, the lattice relaxes non-radiatively. So this is a non-radiative loss process which doesn't involve any defects. So this will still be present in material which is essentially defect-free, as in our single crystals. It also explains why if we cool it down, we depopulate these phonon modes, so we can't really have process 3 occurring then, because we can't distort it as much. And that's why the PL lifetime increases so much. So this will imply that this is an irreversible, unavoidable loss process unless you cool it down. But we found another way to overcome this by applying electric field. So I don't really have time to talk about this in detail, but what this means is that by applying a very small field, we can rip away the charge carriers from the renormalization of lattice and achieve quite long drift lengths. And that means that this material is quite promising for applications which are drift-driven rather than diffusion-driven. And that includes radiation detectors. And we found from this investigation that the limit of detection of bismuth oxide is very low compared to even perovskites and much lower than established materials. So this means that this material is very promising for medical imaging applications, where if you use this as a detector for CT scans, you can lower the dose rate which is required and therefore reduce the harm to the patient. So I'm not going to cover the next section here. Just go back to the key takeaways. So what we found is that some of the key takeaways is that defect tolerance can be quite promising to achieve a new class of semiconductors which can be manufactured cheaply and have defects but still be efficient. And we still believe that having a stable NS2 states at the valence band maximum is conducive towards achieving defect tolerance, but it doesn't guarantee it. And there's more work that needs to be done to understand how defect tolerance arises and how we can generalize this across other materials as well. Now, this bit I didn't really get to talk about, but the main takeaway here is that we've investigated quite a lot into bismuth halide compounds, which we now understand suffer from the problem of carrier localization. And here, we recently found that bismuth oxide is a material that can overcome this problem. And we think that the reason for that is because of this layered structure and this high electronic dimensionality. So just before finishing, I'd just like to thank all the people involved in the works and also the funding sources as well. And finally, thank you very much for listening.
Thank you, Robert, for a very enlightening and full talk. Do we have any questions? Yeah.
Robert, excellent talk. So in sodium bismuth sulfide, do you find the ordered phase? Always you get the disordered phase, what sodium and bismuth is disordered.
Absolutely right. So we have the disordered rock salt phase for this material. Yeah, it is inhomogeneously disordered, Cannon disordered.
So you don't find any ordered phase?
We haven't. Yeah, we haven't tried. We haven't tried to make this material by melt synthesis. And one of the challenges here is that if you heat this material under vacuum, you tend to lose the sodium. Yes. So we found that that's something we have to be very careful about. Right. It's much easier with silver bismuth sulfide, where the silver tends to remain in place in the compound.
Sure. Thank you.
Yep.
Thank you so much. I really like your talk. So I have just two questions. First, related to the electron-phonon coupling. I think this has a really clear signature in the transient absorption, so you can see it. Yeah. And my second question is, converting from like large, you call it, yeah, large bourons to small one. Is it like in consequence, or you can have both at the same time?
Sure. So I'll answer the second question first. You can have both at the same time. So I should mention that large and small polarons are extrema of a continuum, and they really relate to the radial extent of the wave function of your polarons which form. So large polarons means that the wave function is significantly larger than a unit cell, which means that your charge carriers can move a bit more easily, and the charge carrier transfer can be described by the electronic model based on the effector mass. Whereas small polarons means that the radial extent of the wave function is reduced to within a unit cell, and therefore the transport deviates quite a lot from the electronic picture and moves by hopping. But you can certainly have both at the same time, because there's many different phonon modes that can take place in your material, and you get different strength of coupling with those. For your first question, I think about the signatures, sure. I mean, so I think we were quite fortunate to see those signatures with bismuth oxyiodide. Sometimes the other processes which can happen would significantly dampen those signatures, but in the case of bismuth oxyide, this is very clear.
I want to ask. Oh, Tony, yes.
Thanks, Judith. I'm just picking up on Kanishka's question a bit. I'm surprised that you get this sodium bismuth disorder, because there's a strong Coulombic driver to have them sort of ordered. So did you ever do any PDF studies or anything like that to see what the short-range order looks like?
We would have loved to have done some PDF studies. We talked to Andrew Goodwin about this, and he told us to look for the half-half-half peak. But unfortunately, we never saw that peak. And so I think in regards to, it would be a fantastic study to do. In regards to what drives this, I think, so entropically, we would expect there to be homogeneous disorder, where the sodium bismuth alternates in a perfect manner. And the reason they occupy the same lattice site is because they have same ionic radii, so the energy barrier is quite low in that case to prevent this from happening. I think what's the reason why we have inhomogeneous catalytic disorder in this case is because this is a kinetically driven synthesis process. We make these materials as nanocrystals where the reaction temperature and reaction time are rather quite low. So we're driven by kinetics rather than thermodynamics here.
Thank you.
Thanks, Robert. Yes. Behind, yep.
Beautiful talk. Do you have any optical pump terahertz probe data that's consistent with the computational studies of your BIOI materials?
Absolutely. So I have a slide here, which I'm glad you asked. So this is a nice separate work that was involving us, which was done by Laura Hertz using OPTP measurements of this material. So here you can see a comparison. So this is cesium silver bismuth bromide. You can see a rapid drop and then some free carriers, which still are existent. With sodium bismuth sulfur, much larger drops and much stronger carrier localization in this material. But for bismuth oxyiodide, there's no rapid drop. So this is consistent with large polar ions being present rather than small polar ions. And another piece of evidence and consistent with that is if we look at the mobility as a function of temperature, we see this drop decrease as temperature increases. So this is characteristic of large polar ions.
Okay, we better leave it there. So many questions. Thank you very much again,
Thank
Robert.
you.
Beautiful talk.